Before we get too far into the pitfalls of MIDI latency, let's talk a bit about what MIDI actually is and isn't. Now, MIDI is an acronym for Musical Instrument Digital Interface, and it was adopted in 1982 as a protocol for allowing electronic instruments, such as synthesizers, samplers, and drum machines, as well as other equipment such as MIDI controllers, effects processors, and mixing desks, to communicate with each other. Now, we all know that MIDI and audio are two separate things, and one of the key differences between them is that while an audio signal carries a representation of a real-world sound, a MIDI signal carries a set of instructions telling the receiving piece of equipment which action to perform. For example, a note on message tells a synthesizer the specific channel to play on, which note to play, and the velocity to play it at. Another key difference between MIDI and audio is the rate at which the data is transmitted. MIDI transmits data at a rate of 31,250 bits per second, while in the same time frame, 24-bit digital audio at a sample rate of 44.1 will transmit 1,058,400 bits of data. So you can see that compared to digital audio, the rate at which MIDI is transmitted is very, very slow. How long does it take then for one MIDI event to be transmitted? Well, to answer that, let's go back and take a look at our note on message as an example. Like most common MIDI messages, it's made up of 3 pieces of information called bytes, with each byte containing 8 bits. The first byte is called the status byte, and its job is to specify the MIDI channel that the message is to be directed to, which it does with these 4 bits here. These next 3 bits are used to specify the type of operation that's going to be performed, which in this case is a note on operation. And this last bit is always set to 1, and that's to indicate that this byte is the MIDI message's status byte. This next byte is the first data byte, and its job in a note on message is to indicate which notes to be played, and it uses these 7 bits here to specify that. So in this case, the note on to be played is note 60, or C3, and this last bit here is always set to 0, indicating that this is a data byte as opposed to a status byte. And finally, we have the second data byte, and in a note on message, its job is to specify the velocity that the note is to be played at. So in this case, these 7 bits are indicating a velocity of 119. And this last bit again is indicating that this is a data byte. So our note on message is comprised of 24 bits in total. But that's not all. Because MIDI is a form of asynchronous data transmission, meaning that the communication is not constant, it's more of a stop-start affair, a start bit is transmitted before each byte is sent to warn the receiving device of incoming data. Then, after the byte has been sent, a stop bit is transmitted to indicate that the data transmission is complete. So all in all, that makes a total of 30 bits of information to send a note on message. So if we divide the number of bits in the message by the rate at which the bits are being transmitted, we can see that our 30-bit note on event will take close enough to 1 millisecond to transmit. Let's compare this to how long it takes a 24-bit audio event, or what we normally refer to as a 24-bit sample, to transmit. Using the same equation, we divide the number of bits in the sample by the bit rate, giving us a result of 23 nanoseconds. So you can see that MIDI is transmitted at a much slower rate than audio. One audio sample is transmitted every 23 nanoseconds, whereas a typical MIDI event can only be transmitted approximately every millisecond. And when you think about that, it means that 2 notes played on your keyboard at exactly the same time will actually be sent 1 millisecond apart. And on top of this, while a MIDI cable can carry information for up to 16 separate MIDI channels, it can only transmit this information 1 event at a time. So if, for example, a single MIDI event occurs simultaneously on each of the 16 MIDI channels, it will take around 16 milliseconds to transmit them all. So because of its serial nature, unlike audio latency, MIDI latency is not constant, but varies from moment to moment, depending on how much simultaneous data is needing to be transmitted. Now, the term you'll often hear used to describe this moment-to-moment variation in latency is jitter. And one way of reducing this jitter is to make sure that your keyboard is not transmitting any unnecessary data. For example, if your sounds aren't programmed to respond to polyphonic aftertouch, then you'll free up some bandwidth by filtering it out at your controller keyboard. Or if you can't filter specific MIDI events from your keyboard, the next best thing is to filter them from your DAW. And you can do that in Logic here under the MIDI project settings. Any event type that you select here will be filtered at Logic's input and not recorded in the sequencer, freeing up MIDI bandwidth on playback. Another thing to consider is if you use Logic to transmit MIDI timecode, which is very data intensive, dedicate an entire port of your MIDI interface to it, and that'll help avoid timing problems. And you can assign the MIDI port used for MTC transmission just over here in synchronization settings. So by the timing standards that we've become used to with digital audio, MIDI is very low resolution and inherently sloppy. If you expect sample accurate timing from MIDI, then you're going to be disappointed. But for a technology that's around 30 years old, it's really not holding up too badly. So at this point, you may be thinking to yourself, sure, regular old-fashioned hardware MIDI may be sloppy, but aren't software instruments supposed to have sample-accurate resolution? Well, the answer is yes, they are, but only on playback. Whether playing live through either an old-fashioned hardware instrument or a modern software instrument, you'll still be running at the same standard MIDI resolution of one note event, and only one note event, per millisecond. But the low resolution and serial nature of MIDI isn't the only cause of the latency that we encounter when playing through MIDI instruments. So to get a handle on the other causes of latency, we'll need to take a closer look at the MIDI input and output paths. And we'll do that next.